All right, so it's my pleasure to introduce Abigail Polin for our colloquium today. Abby got her BS at NYU and her PhD at UC Berkeley. And already as a grad student, it was really impressive the work she had done. She had many exciting results, including she was able to plot two properties of type 1a supernovae against each other and actually find something new that hadn't been plotted. Everything about 1As had been plotted against everything else for decades and decades. As a grad student, she already found something new that allowed us to distinguish between different progenitor scenarios in a plot I like to call the Polin plot. And on top of that, she also predicted new observables and basically new types of events that were confirmed almost immediately with new discoveries. And you would have thought at that point, a lot of people would have just sort of rode into the sunset, just kept riding that, right? Where you're just producing that theory, comparing with observations. There's many people in our field that would do that, but instead she wasn't dissatisfied to do that. She came to Pasadena as a postdoc with a joint position with Caltech and Carnegie. And, in a lot of ways, she really exemplified what you'd like to see out of a postdoc at Carnegie, where she just really expanded, took advantage of all the resources that we have, expanded into conducting observations to actually try to test some of her predictions. She moved into modeling things like supernova remnants. She just really expanded all the different things she was doing, which was really impressive to see. And it was really fun to have her here. So I'm glad we have her back. Now she's a professor at Purdue. Glad to have you visit. So take it away.
Thank you, Tony. I wanted to start not by science, but by saying thank you to all of you guys, because I really, really love being a postdoc here. I cannot imagine a better place to have done a postdoc for so many reasons. Yes, John paid for us to go on really fun trips to Disney World and postdoc retreats to Lake Ariel. But more important than the destinations were the people. The postdoc cohort here was just everything I could have asked for in terms of people, community, and broadening my mind into new types of science. The professional development was amazing. Having something like the CASI program here led by Gwen was phenomenal. I expanded my abilities, and you get to learn how to mentor students, which turns out is most of your job after this, and something that if you're not careful, you're totally unprepared for. So I'm very grateful for the expanded professional development at Carnegie. And as Tony said, I came here as a theorist, pure theorist. I had never touched a telescope before. But between the pandemic and being here, I thought it would be insane not to learn the observing side of things, right? So I got to do this. And we'll hear more about the science of it later, but I got to go to Las Campanas. I got to see all the wildlife, the good ones, the bad ones. And over my time as a postdoc here, I counted this morning, and basically I've used 6 different instruments on 3 different telescopes, right? Which is just amazing, and something I wouldn't have gotten anywhere else, and something that has made both my science stronger and me as a scientist stronger. So thank you. I really, really love my time here. So now I'm at Purdue. I will be starting as an assistant professor there in the fall. This is my group. So I wanted to put these guys up here because we're not going to talk about all of this today. So I just wanted, especially for meetings, to tell you what else we're thinking about in our group. So Tess is working on a lot of the late phase nebular spectra that we're going to talk about today. Miranda is working on modeling stripped envelope supernovae. Shom, whose work I will talk about today, just graduated. He's heading to UVA as a postdoc. He looks so happy in this picture because it was taken a minute after he passed his defense. And he's our supernova remnant student, and some other miscellaneous topics. But in general, what we do is we think about supernovae from a theoretical perspective, informed by the observations. So this can look like many things, right? The first thing you have to do is figure out what's going to explode. right? In what environment, with what companion, how often, and that's the stellar evolution side of things. Then you have to explode the star, right? We have to run hydrodynamic simulations with full nucleosynthesis. This was my background in early grad school. And so when Tony says I discovered new things about 1As, it was mostly because I didn't know what had been the standard, right? I started from this perspective of the physics of the explosions and tried things, right? So you think it's impressive, but it might have just been ignorance. And then the thing that I'm very passionate about is this last step here of theoretical investigations, radiative transport. So being able to say, here's my model of what we think the explosion physics produces, but this is useless to me unless I can give you something to look for that would tell you if it happens or not, right? And so one of the easiest ways, not the easiest, but one of the standard ways we do this is with radiative transport modeling to produce light curves and spectra of our theoretical models, which we then can work back and forth with the observations to be able to say, do these theories happen in nature? This observing side of things, again, I've been doing a lot of. Carnegie is to thank for that. The Poise group is to thank for that. But I love living here in this space between checking out what's real and iterating our theories and saying, does this work? Does this not work? What should we look for to tell us what's the truth? So supernovae come in many, many flavors, and we categorize them spectroscopically. We categorize them spectroscopically because we have a lot more data than we have ideas. But it's useful to try to separate these based on physics as well. And so today we're going to talk about mostly one half of these, the thermonuclear explosions, the type 1A supernovae, which are those that do not show hydrogen in their spectra, do show silicon, do not show helium, right? All on the same page here. We might touch on some of the core collapse stuff in the end if I have time. Type 1A supernovae, just really quickly, because most of you are not supernovae people who look at these plots as much as I do. So our light curves have a smooth rise, a peak powered by the radioactive decay of nickel-56. At later times, the nickel-56 decays into cobalt-56, which powers this radioactive tail. The spectra look like at time of what we call the photospheric phase around peak here, when there is a photosphere, look like black body spectra with absorption chunks cut out of them, right? For type 1A supernovae, these absorption chunks come from intermediate mass elements predominantly, so silicon, sulfur, calcium, things like that. And how this works is over time, the photosphere recedes, or the ejecta expands and becomes more optically thin. We can see further and further into it. And if we take more and more spectra, we can learn about the composition of the entire explosion. At late times, as the photosphere reaches the core and the entire ejecta becomes optically thin, we reach a second phase, which we call the nebular phase. At this point, we no longer see a black body. We don't have a photosphere. Instead, we see a continuum with cooling emission lines. For type 1A supernovae, these emission lines are predominantly dominated by iron group elements. The results of this radioactive decay of nickel telling us that this nickel here, or confirming that this nickel here is sitting at the core of the explosion. It's our first window into the very inside of the supernova. This is what I'm going to be talking about mostly today, this late time type 1A supernovae, and what we can learn and distinguish between models from these late time spectra. So type 1A are important. I'm going to go through this quickly, but they're important because they're standard candles, right? They also are the predominant iron group element generator in the universe. So it's good to understand them. They're standard candles because typically the most simplistic picture you can think of is that they lie on the Phillips relation. Actually, standardizing them is more complicated than this, but there's a relationship between their maximum brightness, their time at peak brightness, and the width of their light curve. So this is delta F M15. I showed it last slide. It's how much it fades over the first 15 days after peak. So if we see a type 1A light curve and tell how wide it is, we can tell you how bright it is. We can use it as a distance measure. This is a really nice picture. However, it's much more complicated than that. In fact, we care a lot more about the shapes in all bands of these light curves. And it turns out thermonuclear and type 1a supernovae don't only occur on the Phillips relation, right? We have overly bright ones, these 91 Ts, underluminous ones, 91 BGs. We have fast declining type 1as, we have slow declining type 1as, we have other weird thermonuclear transients. So I think that it's important to try to ask ourselves, what is the physics driving these explosions? What happens where? And which of, hopefully this can lead us to which of our 1As are the best to standardize, right, for cosmology. So what do we know theoretically? Type 1a supernova is the explosion of a carbon-oxygen white dwarf. We know this because when you explode a carbon-oxygen white dwarf, you get an elemental structure like the observations tell us exists. We have a core of radioactive material surrounded by intermediate mass elements. And on the outside, you sometimes have some unburnt material from the carbon-oxygen white dwarf, so carbon or oxygen. This right here is all we agree on as a community. Turns out there's many ways to make this happen. There's many different types of white dwarfs we can explode. There are many ways to generate that explosion, and it's highly controversial which happens. I am of the opinion, and it's an opinion, that they probably all do. There's enough evidence and enough diversity in these thermonuclear events that no one model has successfully produced all type 1a supernovae. So the question becomes, which happens when? Are all standard candles the same mechanism? And if not, should they be standardized differently, right? So I like to write on a whiteboard as I go here, but I realize some of these markers might not exist. So we have, I'm going to talk about 3 models today. Yes, look how lucky I am. So the first one is the Chandrasekhar mass model. So this is the traditional picture we teach in textbooks. We have a carbon-oxygen white dwarf approaching the Chandrasekhar mass limit. White dwarfs beyond the Chandrasekhar mass limit can no longer support themselves via electron degeneracy pressure, and they can't exist at a mass higher than this. The original idea was, because there's such a narrow relationship of the Phillips relation, maybe what we're seeing is all these mechanisms are exploding in the same way with minor variation in the amount of nickel it creates, right? So theoretically, the first time we tried to do this, we detonated the carbon-oxygen white dwarf. This didn't work. It created a giant nickel ball that was way too bright to be a type 1a supernova. It was lacking the intermediate mass elements we cared about. So, yes.
You said the first time that we tried to do this.
The community historically.
But we're making models in
Yeah.
bigger codes.
Yes, this was around late 70s, early 80s. The pioneers of the field were people like Stan Woosley, Ken Nemoto.
Right.
Yeah.
But they kind of tended to agree.
Yes, they agreed on this. We still agree on this. If you detonate a Chandrasekhar mass white dwarf, it creates too much nickel. So the second thing that was tried was, instead of a detonation, maybe we can burn the white dwarf with a subsonic burning front known as a deflagration. We all agree, well, this one was not right away. This one took longer for the community to agree that this has the opposite problem. It doesn't create enough nickel 56 to be the normal type 1a brightness. It mostly creates those intermediate mass elements. So the standard for the Chandrasekhar mass model now is to do what's called a delayed detonation, or a deflagration to detonation transition, where first, the fact that we're approaching the Chandrasekhar mass kind of compresses things at the core. It makes it hot, right? You get a little bit of subsonic burning that releases energy into the white dwarf, puffs up that central density, burns some intermediate mass elements. And at some point, that deflagration transitions into a detonation, which then burns through the rest of the star, creates the nickel you want. This can make a type 1a supernovae. However, we don't understand how this deflagration to detonation transition happens. It's just a parameter in codes. And even with the full ability to range between full detonation, full deflagration, and everything in between, we still can't make all type 1a supernovae like this. We have hope. So in 2019, For the first time in the lab, scientists created a deflagration to transition detonation transition that we can observe and learn from. So that's what you're looking at here on the, oh God, I'm not gonna be able to flip it. Oh, but over here in the smaller flip flops. And so what we think is happening is that there's a lot of instabilities in a deflagration. And at some point, all the forces in all these corrugations cause the burning front to snap into a shock wave and transition to the detonation. So people are now working on implementing this into code realistically. But when we achieve this, it will only limit the parameter space that a deflagration to detonation transition can occur in, right? So it will worsen the problem for this model. So Chandrasekhar mass objects can make a 1A, can't make all 1As. We also have mergers. Yeah.
Like how do they do this in the lab?
I think it was a narrow plasma tube. This.
Can reach like sort of the equivalent densities, or is it like a completely different?
Completely different regimes. Yeah.
Sure.
Yeah. So, but it's the best we have. Yeah. It's confirmation that deflagrations can transition to a detonation, which is good. So the next thing we can think about is white dwarf mergers. What if you take two white dwarfs, and the way we breach the Chandrasekhar mass limit is by merging the two? This is very cool, but this time and time again shows that you will have very asymmetric ejecta profiles, which should make sense. You're merging two objects. And spectropolarimetry tells us that most 1As are pretty symmetric. So this is cool. It should happen. Like we have white dwarf binaries that should merge, but has difficulty creating all type 1A supernovae because of the asymmetry issues. The other thing we can talk about is what if, oh, sorry, I want to write mergers over here. We can talk about what happens. Well, if we're not getting this from a Chandrasekhar mass object, we can't go above, let's go below. So how can we explode a subchandra carbon oxygen white dwarf? And the answer was given to us by pretty simultaneously Ken Nemoto and Stan Woosley in the 1980s. And it's known as the double detonation mechanism. The idea here is that you have a subchandra carbon oxygen white dwarf that has accreted itself some sort of helium shell from a companion. The amount of helium will specifically depend on what that companion is, right? Whether it's non-degenerate like a helium subdwarf, a helium white dwarf, or another carbon oxygen white dwarf. There's two of them that they didn't strip all the helium away when they left their core behind. The concept is similar in all three of these though, that helium is a less stable element. It's easier to ignite helium than it is carbon or oxygen. If we can get this helium to ignite, probably along the accretion stream or near where it's accreting onto the shell, you can cause a helium detonation. It will burn around the helium shell. And as it does this, it sends a shock front compression wave basically into the carbon oxygen white dwarf. When that shock front converges near the center of the carbon oxygen white dwarf, it compresses the carbon and oxygen enough to create a detonation. And so then you detonate the full white dwarf. And I told you pure detonations were a problem, but that was in Chandrasekhar mass objects. There's a inverse mass radius relationship for white dwarfs. So decreasing this mass a little bit wildly decreases the central density. So you can naturally get some nickel and some intermediate elements, and you'll vary that based on the mass of the white dwarf you're exploding. So this is what I studied in my thesis. This is what Tony was talking about. Here's a 2D simulation of what this looks like, just so we're all on the same page. Here's that helium detonation burning around the outer shell. You can see the shock front converging towards the center, and I still haven't fixed the jumping for any of you who have seen this, and I apologize every time I show it. And there's your detonation, your thermonuclear runaway. That gives you the type 1A like supernova, maybe. So what we need to look at is, does this actually create the elemental composition we want? Because now we have helium on the outside, right? And the answer is sometimes. Sometimes with very little helium, we get a type 1A supernovae. It has the elemental composition we're looking for. However, if there's too much helium on the surface, and this movie I'm showing you so you can visualize it is a lot of helium on the surface, we create a problem. So during this helium burning, we're actually creating radioactive material on the outside of the ejecta. That radioactive material is not nickel, it's typically radioactive chromium or iron, which has a very short half-life, and it's existing on the very outer shell of the ejecta, so it has a very short diffusion time. So this is not a feature we see in most type 1a supernovae. It would, but the question is, does this happen? Can we look for ones what happens with a lot of helium to show whether or not we should trust it happening with a little bit of helium? I'm going to take us on the lifetime. I'm really going slow here, sorry, but I'm talking fast, so I just included too much. But lifetime of a supernova, I'm going to skip peak because all of our data happens at peak. Most of our data exists at peak. If your model didn't look like a type 1a supernova at peak, we've already thrown it out, right? So we're going to look for features in the weird timings and weird wavelengths of this lifetime of the type 1a supernova to give us a hint of what we're seeing. And I also forgot over here again, subchandra. So let's start with infancy, and I'm going to go really quickly here. The double detonations, some of them look like a normal type 1a, a smooth rise. This is varying the mass of the white dwarf. This is all very little helium on the surface. If we add a lot of helium, that radioactive material on the outside creates an early peak that we weren't expecting and we didn't see in most type 1a supernovae. However, over my time here and over the last couple of years, we've started to discover more and more type 1a supernovae with early bumps. These range from very subtle early bumps to very large early bumps, right? And this could be that radioactive helium ashes that we're thinking about. Unfortunately, it could also be a number of other things. So double detonations make early bumps, but extended nickel distributions that you can create in a weird deflagration profile can also make these bumps. And if we have the right viewing angle and see a supernova running into its companion, that shocking process can create a bump as well. And then you're also seeing into the deeper, hotter ejecta earlier. So there's lots of ways to make a bump. And unfortunately, all of the bump models kind of fit all of the bumps equally well. So a bump is enough to tell us a type 1a supernova is interesting and worth really going after carefully. And it's something we at POISE immediately target as get all the data on this and all the other observing groups too. But it's not enough to tell us what's going on. This was supposed to be skipped. All right. So again, we're not going over peak times, but we can skip to late times. And this is the exciting field right now. So at late times, again, we get to see the innermost ejecta. This is what a type 1a supernova looks like in nebular times. We have, these are the brightest type of 1as. These are the dimmest type of 1as. These are the normal ones. So as we get dimmer, these iron lines grow narrower. The presence of other intermediate mass elements like calcium start to show up more. And in the brightest ones, we really mostly just see these broad iron features, right? I've been thinking a lot about how we can use this core material to test between the two or the three models, since they all vary most drastically in their core. So we'll start with double detonations. Double detonations have an excess of calcium. So these strong features here show up kind of throughout the models. And that looks okay for maybe these dimmer ones, but we're really not seeing it in these brightest type 1a supernovae. However, for a lot of the 1as that we have found interesting early features for, they do show the excess calcium in the later features. And this was the idea that I came to Carnegie with and said, I want to observe more type 1a supernovae in the nebular phase. I want to specifically target ones with good early data so we can go back and forth and ask, is this specific type 1a supernova created by this mechanism or a different one? Luckily, I started working with POISE because the folks at POISE pointed me to another feature that we can look at in the nebular phase, and that is stable nickel lines. So stable nickel is only created in the densest environments. So it naturally occurs, these models are hard to read, but over here at Chandrasekhar mass models, you see we create a lot of stable nickel kind of throughout the ejecta, right? So traditionally we pointed to this and say, if you see a stable nickel line, and this is important because the radioactive nickel decays. So if you see any nickel line, it's from stable nickel a year after it explodes, right? However, it turns out modernly, the subchandra ones also make stable nickel, but they make only about half as much and in more confined velocity spaces, right? Because it's during that convergence process. So the difference in strength and velocity spread of these stable nickel lines can also be used to distinguish between models, right? So awesome, but it's a hard thing to look for. So we have one stable nickel line in the optical, but it's right on top of all of these other blended features, including that calcium line we care about, which is a wildly efficient cooling line. So if there's any calcium there, it just totally dominates this feature. But in the near infrared, there is another very narrow stable nickel line at about 1.9 microns. So the goal, and since Carnegie and Magellan are one of the only facilities where we can do instrument switches halfway through the night, my goal and my aim this entire postdoc has been targeting well-observed type 1a supernovae and getting simultaneous optical and infrared data in the nebular phase. So we can look for, oh, yeah, it's 20 nights, which sounds really impressive, but half of them were weathered. So don't hold me to too high standards here. But 20 nights on mostly Bada, so we can switch between IMAX and Fire. And this is the type of data we're looking to get. And I wanted specifically to highlight one of our POISE grad students who's now a postdoc at UVA, Sahana Kumar, who really, first of all, taught me how to observe in the infrared, but also really helped drive the stable nickel half of this investigation. And she's about to release a paper with a lot of these stable or near infrared type 1As. But this is what we're looking for. We're looking for calcium here, or in this case, stable nickel, which we can be confident about because we see stable nickel of the same velocity spread here. It's really hard to do. It's in a telluric. We have to, after every object, go immediately to a relevant telluric so we can subtract the sky and be confident that we're seeing signal to noise underneath the telluric. It's hard data to get, but we've been getting it. I thought that those were wildly impressive until about a year ago when we got the first JWST type 1a supernovae. And it kind of blows it out of the water, right? Because we have coverage from the optical through the mid-infrared. And in the mid-infrared, there's a lot more stable nickel lines. And they're broader, which we were not expecting. So that's very cool. However, I do want to say for all of you people on tax in the future, JWST does not have good enough resolution for the narrow nickel lines in the near infrared, right? So it is important to do ground-based and JWST simultaneous data. And I've been doing a lot of that with Lindsay Kwok, who this plot's from, and Saurabh Jha, the whole community is coming together and actually coordinating whenever they have a JWST target. We make sure we can get nebular phase in the optical and near infrared as well. So this is the first type 1a supernova we've seen. We observed with type JWST, AEFX. We also have now observed two more, 22 PUL and 22 XKQ, I think. And they're all showing stable nickel lines, but in different velocity spreads. So this is cool. And this is what I'm working on with Tess at Purdue. My graduate student is working on modeling these and actually asking the fundamental questions of how much stable nickel do you need to create a strong line? What velocity spreads do you expect between the two models? And can we combine this to all the other epochs of data to really start hammering home here? I did want to mention, though, with 22 PUL, something totally unexpected happened. This is data. So there's this giant black body continuum in the mid-infrared here that we were not expecting, which has been attributed to dust. But the lines are also very asymmetric. So mergers, which is awesome. I will say 22 PUL is not a typical type 1a supernova. It was overly luminous. It was weird already. We were not terribly surprised that the late time JWST data was odd, but we were not necessarily expecting strong evidence of merger. So very cool. Right. This is a lot of what I'm thinking about right now. This is, I think, the future of type 1a supernovae, because we're starting to be able to look somewhere we haven't looked before, right? And we really don't have a lot of models to compare the data to. Right, there's pretty much the existing models in totality. And I should say these double dets don't have any stable nickel in the network. So we're working blind here, but it's a field you should keep your eye on for the next couple of years. So I have roughly 20 minutes left, and I'm going to jump even older into supernovae. I'm going to jump into remnants. So remnants is a new interest for me. And it's a new interest because of time that I got to spend at Purdue, where I don't know why Tycho's up there. But where we're leading the charge in JWST observations of supernova remnants. I think JWST is also going to change the field of supernova remnants, because for the first time in the infrared, we can see past the shocked material and see what's underneath into the core of the explosion, right? And that core has to be a lot more endemic to the supernova itself than the shock parameters that are happening outside of it. So this is a supernova remnant Tycho. I'm not sure why I put it up there. This is Cassia. This is what I was expecting it to show. So this is Cassia and Hubble. This is a core collapse supernova. This is the Hubble image. I believe Gwen has this on her wall. It's very cool, but there's not a lot here. This is Chandra. We can see the shocked material and the shock interactions. And this is the new JWST, where we can see underneath all that shock material and just this plethora of data that is currently being examined with in the infrared of this gas underneath the shock, right? So the unshocked material in the supernova. We're going to learn a lot from this, but my question was kind of how? What can we learn? How, as a person who likes to compare theory to observations, how can I do in a theory in a way that we can compare to this, right? So, right. How do we go back and forth? This is a model of type 1a supernova expanded out to the remnant phase. This is the remnant. I'm here to, the problem is, if we take any supernova model at all and expand it for 1,000 years, it will look like a remnant, right? We need a way of more than qualitatively going back and forth between models and observables. And you can do this with spectra, but it's really hard. It's really hard data to take. It's really hard data to simulate. So my question was, can we do this phenomenologically from the morphology of the supernova remnant itself? And we think we've come up with a way of doing that. And I'll give you a hint. If I take this simulated remnant and I project it to a mole-wide projection, can you get any ideas of where I'm going? What does it remind you of? It reminds you of the CMB, exactly. So that was the idea. What if we take our models and do power spectral analysis on it? If we go back to looking at Tycho here, there's clearly a preferred angular scale here. Does that tell us anything about the underlying physics of the explosion? If we can look at these power spectra. It worked for the CMB. It worked for the CMB because we had templates where we understood what physics would drive what scales in the CMB. That's what we're trying to build an understanding for in remnants. So, and I think there's a lot of promise here because different remnants, different types of supernovae, this is a 1A core collapse, a pulsar with nebula, they have very obviously qualitatively different structure, right? So there's something to get from this. The question is what? We decided to start with the simplest model for a supernova we could come up with, and that is called a Chevalier self-similar solution. We have one density profile of a supernova running into a different density profile of surrounding medium. This is what that looks like. We get a forward shock over here, a reverse shock down here, and in between, the contact discontinuity becomes this beautiful turbulence, which is called Raleigh-Taylor instability. So the Raleigh-Taylor instability is just a generic thing that happens anytime you have a high density material moving into low density material. It's your coffee and cream instability. Same thing happens in a supernova. You just have a pseudo force with an acceleration instead of gravity, right? So Again, forward shock out here, reverse shock, and the contact discontinuity is where the supernova ejecta is mixing with the CSM, right? This happens in every supernova. This happens in anything expanding into anything else, right? So this is why we started with this, because it's something that happens always. Can we pull it out of the data? So the idea is as follows. Any smooth function can be represented by some sum of spherical harmonics. You can invert this, integrate it, and sum these amplitudes to get a power spectrum, right? To get power for different angular modes. So L is your spherical harmonic mode. It's like pi over theta angular mode. This is what the power spectrum of this image looks like. This is our power spectrum of a generic supernova remnant or self-similar solution Raleigh-Taylor instability. We can break this up into a couple different regimes here. This is a smooth version of that. Over here, I just showed you, these are different resolutions. So these peaks here are my grid scale. Right. What's most interesting to talk about first? Let's start over here, small scale. This is our turbulence. This is our Raleigh-Taylor instability, right? So this is the slope here. It's steep. It's steeper if you're familiar with turbulence. It's steeper than a Kolmogorov cascade, which was peculiar, but okay. We'll get there later. But anything in this regime is washed out by turbulence, right? Anything at all. So if you see anything at these small scales, what you're seeing is the generic turbulence of the supernova interacting with its CSM. Can't learn about anything from the underlying supernova in this regime. In this regime, though, the large angular modes, that's where things endemic to the explosion can be observed. So large-scale asymmetries, nickel bullets, jets, things like this will input power on these large theta modes. And this is what we should look for in the remnant data to tell us something about the supernova. But there's also a transition here, the peak. We call it L naught, the dominant angular mode. And I wanted to know if this dominant angular mode could tell us anything about the supernova. So I ran a suite of models. So these ends are changing the density profile of the supernova. Sorry, it's covered here, but this is running into a constant density CSM. This is a wind. And with a large amount of models, you can see it's totally a mess, right? Except for if instead of plotting this as power versus angular mode, or spherical harmonic mode, I do L over N, so L over the power law of the density profile of the supernova, everything aligns. Everything aligns to have the same L over N, and even wilder, we don't care about what we're running into. That's a little uncomfortable, but very cool. Turns out shocks are powerful, yes.
In terms of physical scales, what are the sort of range of physical scales where this transition happens?
That will entirely depend on your what you'd think this N should be, right? We'll get to this in the real world in a couple minutes. But this was a big clue, right? For the fact that it did not care what it was running into. The only other parameter in this is the profile of the supernova, right? So this dominant scale has to be an indicator of the density profile of the supernova ejecta itself. So something we can diagnose the supernova physics from, which is very cool, because if we go back to thinking about all these different type 1A models, they all have different predictions for what the density profile of their ejecta should look like, especially in the outer edge. So this tells us something about the density profile. What we figured out was it's the density scale height of the ejecta, right? So this can diagnose your density profile and hopefully what type of 1A went off when we compare it to something like Tycho. So it turns out this is just the width of a Raleigh-Taylor finger, which isn't terribly surprising. But these are a number of different models with a number of different of their dominant scales traced out. And so what I'm claiming here is you can see a dominant scale in Tycho. That should be able to diagnose the density profile of your type 1a supernova. With some caveats we'll get to now. So caveat is 2D turbulence, you should never trust it. But I don't need to, because we have Shoham. Shoham is amazing. Students are amazing. I'm so loving working with students. It's the best part of my job. The code I was working with, which was the JET moving mesh code, it's just unwieldy in 3D. I didn't want to do it. I said, okay, I'll put this paper out in 2D, proof of concept. Somebody will get to it eventually. Sham says, I want to write my own code so we can do this. I said, you're in your last year of your PhD. No, that's a terrible idea. But he did it. He showed me wrong. He did it very quickly. He wrote Sprout, a 3D expanding mesh code that's perfect for this type of problem because your mesh expands over all these required orders of magnitudes of supernova expansion over 1,000 years. And with this, he's done tremendous remnant science. So the rest of what I'm going to talk about is Shoham's work, leading into what we can actually learn with this idea of power spectral analysis and supernova remnants. But I want to be very clear, this is Shoham's work. He's phenomenal. He's moving to a postdoc at UVA, and we're all excited. So this is a 3D remnant. So in 3D, first thing first, we confirmed power spectra, same. It was not 2D turbulence. We are still steeper than a Kolmogorov cascade. So what we're seeing is the growth rate of Raleigh-Taylor instability in an expanding medium. In this self-similar case, we are never getting to a region where we're getting a perfect Kolmogorov cascade of turbulence. So this, in retrospect, okay, there's only one scale in this problem, yada, yada. That's what we're seeing here. But we see an L naught that's very similar. I think he scooched it over to 4 theta instead of 3. Yes. But more importantly, he said, we don't think supernovae are power law density profiles. We think a lot of them are a lot more like, for the 1As especially, exponential density profiles. So let's take a look at what this looks like. And this is his modeled X-ray spectra. It's density squared. And here we get something interesting. So by introducing a velocity and time here, we've introduced a new scale into this problem. We've introduced time. So it turns out at early times, we do see this L to the -3 Raleigh-Taylor dominated turbulence. But over time, we do eventually get to a Kolmogorov cascade, perfect turbulence, which is good. So time goes this way. And what you can think of these colors are is blue is a young remnant. It's the start of interaction with the CSM. And red is a set-off time. It is when the reverse shock have totally moved through the supernova, and the supernova has swept up the same amount of mass as what was in its ejecta, right? So that is your transition here. So L naught Y. Okay, I thought I'd show something else here, but that's okay. Our peak scale here still traces the density scale height. It's just the density scale height is now time dependent. Yes, we get our Kolmogorov cascade. So this is cool because this will be, the slope then is something that we can use. It changes with the dynamic age of a remnant. It's something we can look at a real type 1A remnant on and sort of see where in its lifetime we are based on the slope of this turbulent cascade. So again, I said, great, Sham, you did great work. We have a couple supernova remnants with 3D reconstructions. You want to go look at those? If not, like, I'm patient. I have a long career, probably. I hope I can wait for more. And he said, no. We should figure out a way to do what we originally intended, which is take images like this and do our power spectral analysis with the 2D projected images. And again, Sham is amazing. He figured out a way of doing this. So he's doing power spectral analysis now with something called the delta variance method, which if you want to meet with me and talk about, it's very mathy. I'm not going to get into. But the idea is you do power spectral in increasing or decreasing radiuses. So you're just comparing the same projection to the same projection, right? You're deconvolving your projection effects. So he tried it. This is a broadband X-ray image of Tycho. Using the delta variance method, this is the power spectra of Tycho for the first time. We see the L equals -3 slope here. So we are in the young remnant phase, which is good because we've observed a reverse shock. Like we're happy with that. And so what we can do now is in this mode, we can match the slope here to where in the lifetime of the dynamic age in a model where it shows exponential density profile and line it up. We do see a dominant mode here, which relates to the dominant scale, so good. But we can line it up with a model and we see a couple things. First of all, there's a bunch of excess power over here, which is cool. This is what we were hoping for, right? That there's physics going on in this regime that we can learn something about supernovae from, right? That tends to align with, I don't know why I got cut off, but there's an ear in Tycho here. And this is dumping a bunch of power on this scale. I promise you it's not these crosshairs. Everyone asked me that. We masked and unmasked and tested. It's not these crosshairs. I thought so too at first. But furthermore, because we know the age of Tycho, because Tycho saw it go off, we can get some interesting numbers out of this. We can get the tangential, the tangent to the exponential density profile at this time, which I did not write down. I'm going to forget off the top of my head. But we can also get a CSM density in a totally new and untested way. And it's, I think, a factor of like 1.5 higher than other estimates, but still that's shockingly close for a toy model testing this for the first time that we can. So I'm very hopeful for this sort of work in the future. We want to run power spectra of more realistic 1A models, compare them to this. We're going to compare, there's lots of mysteries between the dynamical evolution of Tycho versus 1006. This is the work that I'm most excited about in the next couple of years. Right. We also really should care about core collapse supernovae because they're going to be the supernovae who are not spherically symmetric. They're going to be the ones that are dumping power on those large scales. And I'm hoping this method can start to answer questions between how ubiquitous are jets in core collapse supernovae. If instead of jets, we're getting these nickel bullets. David Vartanen's not here, but I've talked to him about this. That should dump the number of nickel bullets and the size of them and the width of them should have different power scales in these large theta regimes. So we can start to, from a new way, probe the physics of the core collapse supernovae as well. And I'm going to end now and ask for questions, but just my whole ethos right now is we will learn more about these supernovae if we're able to look where we haven't been able to look before, when we haven't been able to look before, and how. So thank you very much. I've, again, really loved being here.
All right, that was great. Questions? Guillermo?
Hi, so this is great. Congrats. So you mentioned spectra is hard for this type of work,
Yes.
but with the local volume mapper project at LCO, we are now getting kind of full data cubes at like sub-parsec resolution for many of these remnants
Yes.
in the Milky Way. And the data, like you look at it and it looks amazing, but are we like very far away from being able to model that? Is there important information there that?
There's a lot of important information there. One of the things that has stymied being able to model there for a really long time is not knowing exactly what part of the ejecta is being shocked and that you are getting a spectrum of. So I'm starting to talk to people like Carlos Bedenes of doing this side by side with that modeling. So if we can dynamically date the remnant, we know a lot more about what part of the ejecta we're getting a spectrum of. So I think we can have some advancements there, but it is hard. Modeling spectra is much harder than doing image analysis.
So this is sort of a follow-on, same kind of question. So there's been some really interesting work done on looking at turbulence actually surrounding quasars and gas surrounding quasars. We have a fellow who's coming this fall to work on this project. She's doing this using spectra basically from IFU cubes. And I think one of the interesting things there is you have velocity information, not even thinking about like composition or anything like that, but just velocity information from the emission lines in these remnants. That's why I have a picture of Cathay on my wall, because that's what I worked on as an undergrad, was measuring these emission lines. And so just the velocity information, I wonder if that encodes something that's maybe easier to deal with.
Yes. So my original hope with this before Sean put together the 2D projections was being able to use something like these strong velocity distributions that we're starting to get from spectra and compare that to the models. I think that is something we have not done in very much. That's what I thought we would do first. But yeah. I don't have to repeat the question if you're handing around the microwave, right?
This is really outside my field, and this is one of the best talks I've seen. Thank you. My question is going back to the Phillips relation. You showed that there is a lot of scatter and there are a lot of things outside the relation.
Yes.
So can we really trust cosmologists?
So yes, and yes. So here's the thing. I make it sound like this giant controversy. However, if you talk to people like Chris and Alan here, it's done very empirically, right? We can pretty easily tell when a 1A is not a good standard candle. I'm just saying I will feel much more comfortable about throwing those out if I understand why they're different.
Ian?
Well, then sort of a follow-up question is, what is the fraction of objects that are initially identified as 1As that do follow the Phillips relation? Are we talking about 1% outliers, 10%, 20%?
I think roughly, this is a hard question for me because I mostly care about the others, but I want to say like 70 to 80% are normal type 1A supernovae. Chris, what do you think about that number?
Depends on how you choose them.
Yeah.
Take a spectra, you get a spectrum and you met a peak, and it's pretty clear what a normal
Right.
thing is. But when you start going into trigonometric,
Right.
that's when I think it
Right, and that's
But-
going to be the future with things like
But then the
LSST.
question is, of what fraction of 1As are used, to follow up on Jorge's question, what fraction are used in cosmology?
Great question. I would need, Reese to publish his data set. I don't know.
So you mean if you find a type 1A and you
How-
spectroscopically classify it, what fraction of the ones that make it into cosmological sample? Say like 2%, and then you throw out the outliers, and there's a whole outlier analysis that goes into
Okay,
this.
well, that's my question is,
Yeah.
what's the fraction of the outliers? 10%?
Yeah.
10% contamination from cosmology.
That would be
Right.
my
Yeah,
guess.
10% is reasonable.
But then we do get into uncomfortable things of, if I could make an identical light curve and peak spectrum with two different models that actually should be standardized differently.
Sure.
Yeah.
So for example, if you do 1As from spiral galaxies and 1As from elliptical galaxies, they standardize differently.
Yep.
Right?
Right. Tell them.
Yes.
So, yeah.
Yeah. So we're getting into statistical numbers of 1As, and with large statistics, we're doing this empirically.
Yeah.
It's just, what is the science behind it?
Sorry, I have a second question. So about scales, like what physical scales, this transition happens. And when you look at this power spectra, what role or how worried you are about the scales in the ISM? Like the ISM has filaments and
Right.
structures and shells and GMCs, right? So depending on where you're expanding, you might see different scales, right?
I didn't include backup slides. We did look into a lot of that, of introducing in the CSM odd anisotropies, and found over and over again that they'd need to be anisotropies at similar density levels to the supernova ejecta itself, which we see when it runs into, say, a star-forming region and lights up a hemisphere, right? So, but for small perturbations, they get totally washed away by the shock.
I mean, they've been expanding for what, hundreds of years?
Yeah.
Right, so that's whatever, 10 to the 9 seconds, so these things are 10 to the 18, 10 to the 19 centimeters, so tens of parsecs
Yeah.
at this point.
Yep. Yeah, I think Tycho is almost spot on 10.
Related question to the density scale height stuff.
Yep.
How many remnants are there that you could start to estimate density scale heights
Yep.
for?
So, yes, in the Milky Way, there's like 8 to 12. But then the question is, can we get good enough at this sort of exercise to move to the Magellanic Clouds or nearby galaxies? We do have observed remnants in those. The data there is good enough to pick up the large scale asymmetries, but not necessarily the finer scaled turbulence.
So like potentially the peak, because it sounds like that's all you need.
Maybe,
for
I,
this.
I hope, but we're starting in the Milky Way.
Did you have a question, Alan? Wait for the microphone.
I'm just trying to see if I took something away that was essential or irrelevant. Did I get the idea that the mapping of the remnants is largely measuring the Raleigh-Taylor scale? You're recovering that, and that's how you get those? Or
Yes.
is it
So
that's just part of it?
the dominance for 1As, because they're so symmetric.
Yeah.
Right. They're not being powered by these weird large scale asymmetries from the supernova itself. What you're mostly picking up is the dominant Raleigh-Taylor scale. Yes.
Neat.
But the size of that dominant scale will depend on the supernova physics itself.
And it does. It varies
Yeah.
all over the place.
Yeah.
That's amazing.
I guess one last question I had is, you focused on Tycho, what about Kepler?
Yeah, that's next.
Okay.
I want to do a comparison between Kepler, Tycho, and 10006 because there are debates there between, especially 1006 and Tycho. 10006 is older but has narrower filaments, and there have been many theories trying to explain this. But I want to know what, if we assume that that difference was created by different 1As,
Mhm.
what would that imply? And
Yeah.
does that make sense?
That's exciting. All right, let's thank Abby again, please.